Hello everybody. If you were in class for this lecture, this is going to be a bit redundant, but we are going to talk about the concept of theoretical plates and where our column bands come through. The last lecture, we focused on diffusion within the column and the dynamics of fusion in the phases of a column, being axillary dispersion, the boundary layer, pore diffusion, and finally surface diffusion. So you're going to want to refer to lecture 4 for that. When we get to the point of talking about theoretical plates, each one of those processes happens in each theoretical plate. So let's go down to banding. We get bands in chromatography when our analyte, which is in the mobile phase, or analytes that are in the mobile phase, move at differential rates of diffusion through the solid phase. So if we see in our example here, if we load our analytes on the top of a column and we start to get bands out, well, each one of those bands is going to represent what's called a theoretical plate. And all of those processes of diffusion that we just talked about are going to happen through each one of those plates. And as these bands move through the column, they're moving through a stack of theoretical plates. Those theoretical plates can be calculated, and we are going to go through that in just a moment. So we have several metrics that we're going to look at for column efficiency. The ones that we are really going to need to pay attention to for the purposes of this exercise are retention time and the width at the peak base. Now, when we inject onto a column, we get a void time. That's the space that's in the tubing before it hits the resin. And then this is the time of the analyte in the mobile phase. But for today's lecture and for the exercise that we did in lab, and what you're going to need to know for our upcoming quiz, retention time and width at the peak base are the most important. So how do we determine retention time? Well, we can use a non-binding tracer. So basically what we do is there's two methods, and this will be coming up in the next couple weeks in this class in a practical exercise on column efficiency. The amount of time in between when we inject a sample onto the column versus the amount of time, or that's the amount of time from the time we inject to the time that we can detect it coming off the column. The way that we can do that to test efficiency on a column is by using a tracer. The two most common tracers we use are acetone, which happens to absorb at 280 nanometers. So we can use our UV detector to measure that. And sodium chloride, a high molarity sodium chloride. Some people use half molar for this. I put down 1 molar because of anything in that range works fairly well. And you can get a conductivity peak through our conductivity sensor on the equipment that we happen to have in the lab. So that's how we would measure our retention time. Is we would load a tracer onto the column and see how long that tracer takes to come off the column. Theoretical plates. Now this is where we're going to get into what a theoretical plate is. If you missed the quick lecture we had on this in lab, you're going to want to pay attention to this. The plate model supposes that the chromatography column, it contains a large number of separate layers called theoretical plates. Separate equilibrations of the sample between the stationary and mobile phase occur in these plates. So all those diffusion phases that we talked about in the last lecture occur through each one of these plates independently as your analytes move, or your mobile phase moves across the stationary phase of the column. The analyte moves down the column by transfer of equilibrated mobile phase from one plate to the next. So we have a diagram here on the right that shows our column, and then if we think about our column being sliced up into theoretical plates, we are getting those diffusion processes of diffusion happening in each one of these plates as our sample moves down the column. These are the phases that we talked about in the last lecture. Axial dispersion, the boundary layer, pore diffusion, and surface diffusion are happening at each theoretical plate as the mobile phase moves through the column. How do we determine the number of theoretical plates? Well, we can do that with a column performance test and some basic math. So the number of theoretical plates is just an index to determine how effective our column is going to be at separating our analytes in the mobile phase out from one another. It's an indirect measure of peak width for a peak at a specific retention time. So we're going to need retention time and our base peak width in order to do this calculation. The column efficiency is a function of the dimensions, flow rate, compound, and retention. For column comparison purposes, the number of theoretical plates per meter is often used. So it's the number per meter is the standard that we would use in a process column chromatography when we're talking about big industrial scale processes. The formula that we are going to be using is n equals 16 times the retention time over width at the base squared. 16 is a mathematical constant that was derived by using the column at the width, the peak base width. There is another constant that's 5.54, I believe, that you can use if you want to use the half peak width, but we're going to stick with the base peak width just for consistency here. But just so you know, there is another way to measure it using the half peak width. So the number of plates equals the length of the column over the height of each theoretical plate. For this column example shown on the right, we have a column that is 10 centimeters long and contains 50 theoretical plates. So our n number is 50. We have 50 theoretical plates. We have a 10 centimeter long column. So our height of each theoretical plate is 50 over 10 centimeters, which equals 0.5 centimeters or 0.005 meters per theoretical plate. Now, this is where we put the math together. Our retention time is 4 minutes. This is just an example. Our peak width at the base is 2 standard deviations. So, using this formula, we simply plug in our retention time and our peak width. Since it's a Gaussian peak, that's why I use the example here of 2 standard deviations, because what we're measuring is we're measuring across the z-score at the bottom of that distribution. So if we do the math here, we get n equals 16 times 4 divided by 2 squared is 64 theoretical plates. So now if we take that math and plug it in, we can figure out what the height of our theoretical plate, or each theoretical plate, is. So we've got 64 theoretical plates across 10 centimeters, which is 0.1 meters. So if we just Do simple math. 64 plates divided by 0.1 meters is 640 plates per meter. Now, this is important because this gives us our resolution factor in chromatography. Resolution just measures how well two peaks are separated in a chromatogram. So if you could imagine that each one of these peaks is moving across those theoretical plates down a column, that's why column efficiency and these plates are important in our process. It's calculated by dividing the difference in retention time between the two peaks by the average width of the two peaks. So resolution is presented by the letter R in a chromatogram, and higher resolution means the separation was successful. So if we look at our peaks on the left in this diagram, our resolution factor is 0.8. Well, that means that any resolution factor that's under 1, we're getting basically a contamination right in the middle of these two peaks where they are not being well separated. Resolutions above 1, we're starting to see efficient separation of our peaks on the chromatogram and in our fractions coming off the column.